Systems of equations is what we're going to be dealing with. According to the math department, we're supposed to cover sections 12.1, 12.2, 12.4, then 12.6, 7, and 8. I'm going to forego section 12.1 because it's solving them by hand. And you have a $100 calculator that you own. Let's use it. Okay, so solving by substitution, elimination, or graphing with linear systems of equations is a valid method, no question about it. But it's not something that I think you would even do. I mean, if you've got the choice and you got the calculator in your hand, you're going to use matrices to do it, which is what I'm going to focus on for the most part this evening. Is matrix algebra and matrix solving the systems equation. So we're going to start in 12.2 with systems of equations. All right. There are 3 scenarios with any system of equations, whether it's got 2 variables or 26 variables. There are only 3 scenarios that can happen. The first one of those is the most common, is that there's one solution. If you were graphing, that would be one intersection. We're not graphing, but if you were, it'd be where the lines cross. That's what it is. The second scenario is that there's no solution. Thus, no intersection. If you're dealing with linear systems, that would be parallel lines if you were graphing these things. So to visualize something that had no solution, you think about parallel lines. They never cross. One solution is going to be 2 lines that cross somewhere. And then the third scenario is infinitely many. And if you're graphing, they would be the same line. And when we get to 3 variable systems, it'd be the same plane, or it'd be planes intersecting at a line. There's a couple different scenarios that could be. But if you're talking about linear stuff, one solution is where 2 lines cross. Any thing that doesn't cross is no solution, and then the infinitely many is the exact same line graphing on top of each other. Like I said, we're not graphing, but be able to recognize those sort of things there. That's what would happen. So maybe a sketch would be a good thing. So there's a coordinate plane. You could have a line 1 and line 2. That is our solution, is where they cross. That's what I'm trying to illustrate here. No solution. Line 1, line 2. They're parallel. They never cross. And then infinitely many. It's the hardest one to draw. Draw that line, and then the other one is a line right on top of it. It's touching it infinite number of times, so that's the infinitely many solutions idea out of that. So these are the linear graph scenarios. The 3-dimensional graph scenarios, nobody wants to draw those. They're very difficult to draw, but we can visualize those when we get to it. I'll show you how we can use a nice binder to do that with. It's pretty easy. So let's start with an example. We're going to solve the system of equations, and I want to show you how to do it with matrix. So x plus 4y equals 14, and then 3x minus 2y equals 0. So a 2-variable system. You could do this by elimination if you wanted to, or substitution. Those are valid methods. They require a lot of moving of variables and multiplying or adding, subtracting. A lot of places for mistakes to happen. So one of the better ways to solve is to convert that into a matrix. And for this one, we're going to convert it into a 2x3 matrix, 2 rows by 3 columns. So the first number, when you talk about size of matrices, is rows by columns. So this is 2 rows, and you take the coefficients that are in front of your variables. So we have a 1 in front of x, a 4 in front of y, and then the 14. And then we have 3, -2, and 0. What that's actually called an augmented matrix because it has the what the equations are equal to in it. It's called an augmented matrix. And you'll see some textbooks will put like a line right there, or they might put a colon in that row just to separate what the equations were equal to with the coefficient matrix. It really does, and then other textbooks don't put it at all. So depending on what version of or author you have, deciding what they do. So what we're going to do is we're going to use our graphing calculator to help us do that, and we're going to do this operation called RREF. What that stands for is reduced row. I hope I spell echelon right. I think this is correct. Form. Reduced row, RREF, reduced row echelon form. You might also hear that called Gauss-Jordan method for solving a matrix. It's all row operations is what it does. So with the graphing calculator, this is what you're going to want to do. Okay. So normal calculator screen, you want to go to the matrix menu, and to get there, you're going to hit second and then the X inverse button. And you've got the first menu that comes up is names. That's when you go to use one of them. Okay, so you could grab one, but we're going to edit one. So we need to go over to edit. We hit second and then X inverse, which is the one that's highlighted in red there. It should say matrix above it in blue there. Got it? All right. So go over to the edit menu, and then you're going to pick one of those. I'm going to pick A because it's the quickest one to get to. And then I tell it what size that matrix is. And in this one, it's a 2 by 3. So 2, enter, 3, enter. And it should resize that matrix to the correct size. And if yours has all zeros in there, that's wonderful. If yours has some other numbers in there, it doesn't matter. Mine's got a bunch of stuff in there. I'm going to get rid of it in a second. Okay. So from there, you're going to enter in that 2 by 3 matrix that we wrote on our paper. That the first row was 1, 4, 14. So 1, enter, 4, enter, 14, enter. You don't have to delete anything. Just type over the top of it, and it overrides it. And then the second row was 3, -2, and 0. Everybody with me up to that point? So if we went to matrix, we went over to edit, we picked one of the matrices to use. I picked A, went in there, changed it to a 2 by 3, and then entered the matrix, the augmented matrix from the problem. Once I've done that, I hit second, quit, or mode. So go back to the regular calculator screen, and I want to do the reduced row echelon form of that matrix. So I'm going to hit second, and then the matrix button again. Then I'm doing some math with that matrix. I'm going to go over to the math menu, and then I'm looking for RREF. The quickest way to get there is just press the up arrow, and it's because it's down toward the bottom. RREF, and enter. And then we need to tell it what we want to use RREF on. So we want to pick the matrix. The matrix I put in was A, so I'm going to pick matrix A. You don't have to close those parentheses. You can, but you don't have to. And then hit enter. And it cranks out the reduced row echelon form of that, which the reduced row echelon form has 1s and 0s in the coefficient side, and then the solutions are in the last column. Okay, so RREF produced this 1, 0, 2, 0, 1, 3, and I'll put that line there because I think this textbook's author does put it there. What this means is this row says that X equals 2. The second row says Y equals 3. So we get x equals 2, y equals 3, ordered pair form 2, 3. The ordered pair form is what we're going to go for here, is an ordered pair. All right. This, on this, the left-hand side, the 1, 0, 0, 1, is actually called an identity matrix. We'll get into that in another section tonight, but it's pretty straightforward, a lot simpler than, may take a while to type in. You guys are usually quicker at typing in than I am, but because you can use your thumbs, and I get one click at a time. So let's look at a larger matrix. Maybe a 3-variable matrix. 2x minus y plus z equals 0. X plus z minus 1 equals 0. And x plus 2y minus 8 equals 0. So this one is a little screwed up because it's got some stuff that doesn't have a variable on the left side and things that do have variables on the left side. And it's got 3 variables in it. So what we want to do is rewrite this so that it's kind of in the right form, where you got all your variable stuff on one side, your numbers on the other. So the second row, the second equation there has got that minus 1 in there. So we need to move that over. I'll put plus 1, and that's going to change it to x plus z equals 1. The top row's fine. 2x minus y plus z equals 0. And notice how I'm kind of lining things up here. X is, and I'm almost making it look like a matrix now. And then on the third row, I got to move that 8. So it's going to be x plus 2y, no z's involved, and an 8. So this is a 3-variable system, even though a couple of the equations don't have 3 variables. So when we set up our matrix for this, it's going to have 3 rows because there were 3 equations, and 1, 2, 3, 4 columns. A column for x, a column for y, a column for z, and then the augmented column, which is what they're equal to. Okay. So your first row would be 2, -1, 1, 0. Second row is 1. There are no y's in it, so I'm going to put a 0 in that place. Then a 1 for the z, and the 1 is what it's equal to. And then the third row has a 1 for x, a 2 for y. There aren't any z's, so I'll put a 0 in that place, and then an 8. So I have a 3x4 matrix there to work with. So what I want to do then is do the Gauss-Jordan or the reduced row echelon form on that matrix. So I've got to put that matrix in my calculator. So second, x inverse, over to edit. I'm just going to go into matrix A again, change it to a 3x4, and then put it in there. 2, -1, 1, 0, 1, 0, 1, 1, 1, 2, 0, 8. Check. Go back through and check to make sure. 2, 1, 1, -1, 0, 2, 1, 1, 0, 0, 1, 8. Okay, so everything's right. Go back to regular calculator screen. And here's the great thing about the graphic calculator. Instead of having to hunt through and find RREF again, I can just press arrow up and pick up that. Since I use the same matrix again, I don't have to go hunt through and find it. I can just press up and grab it and hit enter. And it spits out a reduced row echelon form matrix. And 2, 3, -1 is a solution there. 1, 0, 3, 0, 0, 1. So that gives us the ordered triple this time because it's X, Y, and Z, 2, 3, -1. Okay. Second. Enter, and then grab second matrix. Did you just copy and break it? That's why. Yeah. Yeah, because it, although that would be really nice if it would recognize that. I would love for it to be able to do that, but it can't for whatever reason it doesn't. So, all right. Okay. So there's our ordered triple as an answer. And the good thing about the matrix answers here is the fact that we can take that and if it were to give us decimals as answers, we could get it to convert those into fractions for us. We could just hit math, enter, and that would convert any decimal answer that you got into a fraction. Whereas solving by graphing, it really can't do that at all. And you just got to get estimates as to where it's at. So that's another plus to that. Let's look at another system. Kind of get some of the special things happening here. 6x minus y minus z equals 4. Negative 12x plus 2y plus 2z equals negative 8. 5x plus y minus z equals 3. And let's go through setting up that system. So set up a 3x4 matrix again. 6, -1, -1, 4. -12, 2, 2, -8, 5, 1, -1, 3. That's the matrix that we need to enter into our calculator. Put that up there. Second matrix. Edit. Already got a 3x4 in A, so I'm just going to use it again. 6, -1, -1, 4, -12, -8, and then last row 5, 1, -1, 3. -1, -1. All right. So we got that matrix in there to run RREF on. So again, you could arrow back up to RREF, or you can hit second matrix, math, find RREF. Whichever one you're quickest at. Matrix A. And here's one of those that got some decimals in there. It's pretty ugly there, and if you round them, it's not going to be exactly right. So let's convert that into fractions. So we're going to hit math, enter. So we've got this matrix as our solution matrix, but look at that bottom row. That bottom row has what? Well, it's got something there. Bunch of zeros. That bottom row is all zeros, and the bottom row tells the tale on these systems of equations. The first two that we did had one solution because we found the x, y, and then the x, y, and z for that. Here on this bottom row, if it's all zeros all the way across, all four of them, then what this means is it's infinitely many solutions. Yes, the bottom row is the one that decides all that stuff. The way your calculator and any other person does reduced row echelon form, that bottom row is going to end up telling you what's going on. If it's all zeros, then it's infinitely many solutions. If it's all zeros and then something else here, then that's no solution. Okay? We'll do an example of that a little bit. But, we're not done with this one yet. We got to do some work. Because just saying it's infinitely many solutions, that's wonderful, but it doesn't tell us what kind of solutions there are. There's infinite number of solutions, but they're a certain kind. So what we're going to do is we're going to write the solutions in the form of z. You knew it couldn't be this easy. So they're going to tell you which variable to have in your solutions. When they say write your solutions in the form of z, they mean, okay, I need x to equal something that has z in it, and then y to equal something that has z in it. If they say write the solutions in the form of y, that means you need x to equal something with a y in it, and you need z to equal something with a y in it. So but normally in Math 140, z is the letter they're going to tell you to use. On the final exam, that's the only letter I've ever seen in several years of teaching this course. This Z for you to do that, and pretty sure that's the only one I'm going to ask you to do too. All right. So what we do is we take them from this solution matrix here. We're going to take those equations back out of there. So that's actually x minus 2 over 11z equals 7 over 11. And then that second row is actually y minus 1 over 11z equals negative 2 over 11. These are pretty easy to get z form on, because to get x by itself on this first equation, all I got to do is add 2 over 11z to both sides. All right, and that's going to give me x equals 2 over 11z plus 7 over 11. And this second one, to get y by itself, I just add 1 over 11z to both sides. And there I've got y by itself. And then they're going to write it in an ordered triple form, where you've got x 2 over 11z plus 7 over 11, y 1 over 11z minus 2 over 11, and then z is just z. That's the final solution to that, is in ordered triple form. This represents y, this represents, or x and y, and then z is last. What that does is, if you could pick any z and plug it in there, and you'd get a different x and y value for every z that you picked. So the infinite, what this is these are three planes that are intersecting at a line. So it's like, book's a good example. You've got three planes. This is one plane, cover of the book. This page is a second plane. Right now, those two are intersecting where the spine of the book is, right? The spine of the book is a line. Okay, so there's an infinite number of places that they're touching, right? If I add a third plane in there, a third equation, just another page, they're still intersecting at a line, right? That line has an infinite number of points on it. And this order triple is like a representation of that line, that I could pick any z value and get a y and an x value that goes with it on that line of that. So that's what they're having you do here. Like I said, z is the most common letter that you're going to have to solve for, and it's one step. Not really incredibly difficult stuff to get z by itself. Let's look at example D. Here's our system: x plus y plus z equals 6, 2, x minus y, minus z equals 3, and then x plus 2y plus 2z equals 0. Okay, so there's our 3 variable system. Notice we're doing more of those, not too many of the 2 variable systems because they're boring and too easy out of there. So throw that into a matrix. 1, 1, 1, 6, 2, negative 1, negative 1, 3, 1, 2, 2, 0. And then run RREF on that. Matrix. All right. Again, you should be seeing something different happening on that bottom row. Again, the bottom row is the one that decides everything. It's got all zeros in the variable columns, and then this one has a 1 in the fourth column. It could be any other number. It doesn't have to be a 1 there. But the key is that it's all zeros here. And then that tells you, the 1 tells you, oh, it's all zeros equal to some other number. Does 0 ever equal any other number? No. So these are the easiest ones. That right there tells you that it's no solution. And then there's nothing else to do. That's my favorite ones. Other than the ones that have one solution. One solution is going to happen the most. So if you're doing practice problems or you're doing the Canvas quiz or anything, that should happen most of the time. No solutions and infinite minis don't happen near as often. Okay, so those are more rare situations for that. So, excuse me. Sorry, they're really loud. I'm sorry. My wife complains that they're super loud. Yeah, that's funny. All right. So in the same section, let's talk about doing some row operations by hand. It's not something that you're going to have to do to completely solve out a system of equations by hand, but being able to do a given set of row operations by hand is something that the math department really wants you to be able to do. So we're going to show you a row operation by hand. It's really easy. You just got to be able to follow directions. So here's a matrix. They'll give you a matrix to start off with. Let's do a small one. 5, 2, 13, negative 3, 1, negative 10. All right. And put the line there because our author does that. Okay. Now, complete this row operation. 3 R1 plus R2 equals R2. What that tells us to do is to take 3 times everything in row 1 and add it to row 2, but then only change row 2. What it's equal to is the row that's changing, okay? So we're doing 3 times row 1, but in our answer, row 1 is going to be 5, 2, 13. We're just going to use 3 times row 1 to add to row 2. And then whatever it's equal to, that's the row that changes. That's the key to the row operations, is that whatever it tells you it's equal to, that's the row that changes. So row 2 is the one that changes. So when I do this, I'm just going to copy down row 1 because it's not changing. Row 2 takes 3 times row 1 and adds it to row 2. So each individual piece, each element, so 5 times 3, 15 plus negative 3, 12. That goes in the first spot. And then you do 3 times 2, 6, plus 1, 7. 3 times 13, 39, plus negative 10, 29. And we've completed that row operation. That's not hard at all. I mean, it really is just following directions. If it gave you more than one row operation, you do them in order that they gave you. So they give you first row operation, do it, get the answer. Then take that answer matrix and do the next row operation. So like if they said, do this row operation, and then the next one said, take that matrix and then do negative 2 row 2 plus row 1, change row 1. Maybe they had 2 operations to do. So we would take this answer and do that same thing. So if we're going to do that row operation, we'll copy that and put it on here. That same row operation on that new matrix is what we're doing. So which row is changing? Row 1. So I'm going to copy down row 2, 12, 7, 29. So then I say negative 2 times row 2 plus row 1. So negative 2 times 12 is negative 24 plus 5. Negative 19. And then negative 2 times 7 is negative 14 plus 2, 12. And negative 2 times 29, negative 58 plus 13, and this is the answer after that row operation. And then I could give you another one, and just they're not going to give you probably more than 3 at a time. But the idea is you do one of them, get the answer, then do the next one, get the answer, and then if there's another one, do it on the answer. Okay? And the row that changes is the row that it's equal to. The rest of them stay the same. So this is really what your calculator is doing when it's doing that RREF. It's doing a bunch of row operations in very, very short amount of time to get the matrix into that 1, 0, 0 answer, 0, 1, 0 answer. That's what your calculator is doing when it's doing all that fun stuff. Another thing that's kind of operational with this section is the matrix inverse stuff, and that's what I'll save that for this next section since we've already done the row operations. Let's do 12-4, and then I'll put the inverse in with it, because you really don't use the inverse too much on solving systems. It's more of a just find the inverse of this matrix kind of deal. So section 12-4, we're almost halfway with the chapter, matrix algebra. Some of this I do with the calculator, some of it I do not. So we'll show both ways on everything that I do with or without a calculator. Adding and subtracting. Matrix algebra just means doing some operations with matrices. If you're going to add or subtract matrices, let's say we had matrix A was 3, 6, 5, -7, 2, 10. What size is that matrix? 3 by 2. That's important. Say matrix B. 1, -2, 11, 8, -5, 14. What size is that matrix? 3 by 2. 3 rows, 2 columns. Okay. In order to add or subtract matrices, they have to be the exact same size. If they are not the same size, it's an undefined operation. That's what if they're not the same size, then you would call it undefined. These two are the same size, so I'm going to be able to do the addition and subtraction with them. But they have to be the same size to add and subtract. That's not the same rules later on. Okay. So adding and subtracting got to be the same size. So example A, if we took matrix A plus matrix B, this is one of those things that I normally don't do in the calculator just because it takes me too long to type them in, and I can add and subtract numbers pretty efficiently without typing all that matrix into the calculator. When you add and subtract matrices, they have to be the same size because you're pairing up the elements that are in the same spot. So the 3 in the top left goes with the 1 in the top left there. So you add them up. 3 plus 1 is 4. And then 6 goes with -2. 6 plus -2, 4. 5 plus 11, 16. -7 plus 8, 1. 2 plus -5, -3. 10 plus 14, 24. And notice we get a 3 by 2 matrix back. Same size, didn't change size when you add and subtract, doesn't change size. It should stay the same. You can type those into the calculator and have it do that addition. I'll show you how to do that real quickly. It's really easy. So go to the matrix menu, go over to edit, and this is a 3 by 2. And I'm going to enter that in 3, 6, 5, -7, 2, 10. Then I go back to matrix, edit, I need matrix B to be a 3 by 2. And you can see why I don't do this with the calculator, because it takes so long to enter them in. I could have just done the work. But if it gets to be like crazy numbers, maybe it's helpful to do this. I don't know. All right, so once you got them typed in there, all you got to do is go grab the matrices you want to add together, A plus B. So second matrix A plus second matrix B. And it spits out the exact same thing that we did by hand. Same thing with subtraction. Do the same. You can get it to do the same thing. So if we did example B, we did A minus B. 3 minus 1 is 2. 6 minus -2 is 8. 5 minus 11, -6. -7 minus 8 is -15. 2 minus -5, 7. 10 minus 14 is -4. Subtraction. Great thing about the calculator is I could go up here and just grab that operation and then go in here and just change that to a minus sign. And I get the same thing back out of that. So you can use the calculator to do the addition and subtraction. I usually don't, though. No matter what size, in order to add and subtract, two matrices have to be what? The same size. No matter how big or small they are, they've got to be the same size to add and subtract them. All right. Next thing in matrix algebra is this thing called scalar multiplication. Scalar multiplication, fancy word for distribute. kind of like distributed property. The only thing is it's not distributing across addition or subtraction. It's distributing a number across a matrix. That's the only difference. So if you've got a matrix A, and we'll use that same one. We could use this 3, 6, 5, negative 7, 2, 10. Same one we had a while ago. And a matrix or a scalar multiplication upon that matrix might be something where they say negative 3A. All that means is you take negative 3 times that matrix. So times 3, 6, 5, negative 7, 2, and 10. What that's going to do is just multiply each individual element by negative 3. That's negative 9, negative 18, negative 15, positive 21, negative 6, negative 30. And there's your scalar multiplied matrix. So it's like distributed property. You just multiply everybody in the matrix by the same number. It's scalar multiplication. What they like to do is mix that with addition and subtraction. Okay, so if you're going to mix that with addition and subtraction, let's throw in that same matrix A that we had from example A and B, and matrix B that we had. So matrix A, and then here's matrix B. I didn't copy all of it. Why not? Oh well, I'll get all again. Still be listed, right? So there's matrix B. The 1 there. And what they'll ask you to do is something like do 2A minus 4B, where you're doing scalar multiplication mixed in with addition and subtraction. So when you're doing that, the scalar multiplication happens in order of operations before addition and subtraction, just like it does with regular numbers. So you would distribute 2 to all the elements in A, and then distribute 4 to all the elements in B, and then subtract those answers is what you're going to do there. So that ends up being 2 times 3 is 6. 6 times 2 is 12. 10, negative 14, 4, and 20. Minus, and then I'm just putting a 4 through that guy. 4, negative 8, 44, 32, negative 20, and 4 times 14 is 56. And then subtract those. Now, I'm doing this by hand, but we're going to do it with the calculator too. 6 minus 4 is 2. 12 minus negative 8 would be 20. 10 minus 44 would be negative 34. Negative 14 minus 32 is negative 46. 4 minus negative 20 would be 24. 20 minus 56 would be negative 36. And there's my solution of that. I've already got matrix A and B in my calculator. I've already typed those in, so I can get it to just do that in one little job here. 2, second matrix A, minus 4, second matrix B. And we get that same solution there using the calculator. So you can use the calculator to do that very easily. It doesn't take too much. Now, so addition, subtraction, scalar multiplication, those are the operations I normally don't do in the calculator. I usually do those by hand. I showed you how to do them with the calculator because you can, but I normally don't do that with the calculator. I usually do that by hand. Let's look at one that I used to do a lot by hand. I don't do it anymore just because it doesn't really help much. That's multiplying matrices. When I took a linear algebra class, if anybody's going to school to be an engineer, you'll take linear algebra. You'll have to do some multiplying matrices by hand in there because you'll have variables in there, and it's fun. and really builds character. That's what that's what my professor told me. It's building some character here, really. And he said, yeah, really. And turns out I do appreciate the calculator much more now because doing it by hand stinks. So when you're dealing with multiplying matrices, these have a different set of rules than addition and subtraction. Addition and subtraction, the matrices have to be exactly the same size. In multiplying matrices, you don't want them to be exactly the same size. You've got when you multiply matrices, you got row by column is how the size is decided, right? Row by column. And then you're multiplying times something else that's a row 2 by column 2. So this is row 1 column. So first matrix on the left, the right matrix, we're calling it matrix 2. What has to happen here is these two have to match. This has nothing to do with getting the answer. This is just deciding, can you even multiply them? It's like the addition rule where they got to be exactly the same size. With multiplication, the columns from the left matrix have to match the rows from the right matrix. Okay, these must match. Doesn't matter what the row from the left matrix and the column from the right matrix are. It doesn't really matter. It all is about the columns from the left matrix, the rows from the right matrix. A legal multiplication would be a 2 by 3 times a 3 by 4. Because these two match, that's legal. The answer that you get will be a 2 by 4 coming from the ends there. And so multiplying matrices is a much different animal than adding and subtracting them is. It's very, very different. Now, I'll show you how to do it by hand, but I don't think it's going to help you very much. But just in case your calculator dies and you need to know. So here's a matrix: 2, 4, -1, 5, 8, 0. And matrix B: 2, 5, 1, 4, 4, 8, 0, 6, -3, 1, -2, -1. Yay. All right. Now, nice large matrix there, and not such a large matrix there on A. So we're going to do example E, matrix A times matrix B. Order really matters in matrix multiplication. Matrix multiplication is not commutative like numbers are. Regular numbers, 2 times 3 and 3 times 2 is the exact same thing. Matrix A times B and B times A are not the same thing. Okay, so even if it is defined, they're not the same answer. So matrix multiplication is not commutative. Got to keep that in mind for if you ever go any further than this mathematically. All right, so what size is matrix A? 2 by 3. Matrix B, 3 by 4. All right, is that legal to multiply? Yes, those match. So what size is the solution? It's a 2 by 4. Okay, now 2 rows, 4 columns. Doing this by hand, I'm just going to kind of walk you through it here. You don't have to do this. Okay, it's row by column. So you're taking this row times this column and adding it up. It's not something I'm going to ask you to do. I mean, 2 times 2 is 4. 4 times 4 is 16. And -1 times -3 is 3. So we got 4 plus 16 plus 3. So the first element would go there. That's sum. And then you would take this row times this column and do the same thing. 2 times 5 is 10. 4 times 8 is 32. That's 42. -1 times 1 is -1. So that would be 41 would go in the second column of the first row. Then you take the first row times the third column. 2 times 1 is 2, 4 times 0 is 0, negative 1 times negative 2 is 2, so we got 2 plus 2 is 4. So the third column of the first row is 4. Then you take that first row times this column, and you keep going and do that for the whole time. It is not the when you go to linear algebra, the matrices are not this small. These are small. Okay, so just so you know, if you're gonna be an engineer, you got something to look forward to. They're not; these are small matrices compared to what I had to do in that class. It was bananas. So let's do the multiplication with the calculator. So go to matrix and let's enter those matrices in as A and B. So you can see how many operations. I just didn't get through the first row times the columns, and I'd already done like, okay, so 3 by 4 or 3 by 3, and that's 9. 4, 12. It's 16 operations per row to get answers. That's nuts. So we got a 2 by 3, and I'm putting that one in. 2, 4, negative 1, 5, 8, 0. Okay. And then go second matrix, edit matrix B, and it is a 3 by 4. 2, 5, 1, 4, 4, 8, 0, 6, negative 3, 1, negative 2, negative 1. Yeah. All right. So got those matrices in there. Then I'm going to tell my calculator to do the matrix A times matrix B. So second matrix A times B. There we go. 23, 41, 4. Oh, yeah. 23, 41, 4, 33, 42, 89, 5, and 68. I have seen problems on the final exam where you didn't actually have to do the multiplication. They just wanted to know what's the size of the answer. So knowing that theory about the matching the columns and rows, and then knowing that the outside pieces are your answers there are important. So there's our solution to that. Example F is B times A. Yeah, so it's 3 by 4 times a 2 by 3. But they don't match there, so that's defined. That's the key there. Again, matrix multiplication is not commutative. It is not commutative. Very, very much not commutative. All right. Now, a little more stuff. Identity matrices. All right. Identity matrices are of various sizes. I2 is what it's called. Is a 2 by 2 matrix with zeros and ones in it. It's got a diagonal of 1 starting at the top left and going to the right, bottom right. I3 is 3 by 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. And we could continue this on to I4 is a 4 by 4 matrix. Oh, be real happy there. And we see we could continue that to I5, I6, I28 if you needed to. I don't think you'll ever need that, but the identity matrix, what it's useful for is matrix inverses. which is where we're headed next. Almost headed there too early a while ago. A matrix inverse. Say we have matrix A, 1, 1, 0, negative 1, 3, 4. Let's make those too small. 0, 4, 3. What size is that matrix? 3 by 3. In order for a matrix to be invertible, i.e. have an inverse, it has to be square, meaning it has to have the same number of rows and columns. Okay, 3 by 3, 2 by 2, 4 by 4, 16 by 16. Those are normally invertible. Not always, but in order to even be possible, it's got to be square, meaning it's got the same number of rows and columns. Okay, now the manual way to find the inverse is to take this identity matrix that goes along with that. What identity matrix matches up with matrix A? I3, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. And then you put the actual matrix A. 1, 1, 0, negative 1, 3, 4, and then 0, 4, 3. And what you end up having to do here is do row operations. To flip the matrix. And by flip the matrix, I mean take this side and make this side look like it. So do the row operations that would put a 1, 0, 0, 0, 1, 0, 0, 0, 1 over here. That would change these values. Now, you don't have to do that by hand. That takes a while, and I would say it takes a fair bit of talent to do it efficiently. Some people can do it quicker than others. Not saying that everyone can't do it. It can be done with just enough perseverance. You can make it through. But there's a better way, and it's your graphing calculator. To find that inverse, you're going to take that matrix A and put it in your calculator. I'm going to go to my calculator, go to matrix, edit. Matrix A is a 3 by 3 now. 1, 1, 0, negative 1, 3, 4, 0, 4, 3. Okay. Once I've entered that matrix, I want to use that matrix name. So second matrix, and it's just like if I were going to multiply or add or subtract it. I got to go get the matrix I want, matrix A, and I want to find the inverse. Your calculator has an inverse button. It's that X to the negative 1 button that's right there. Bless you. So I hit that button and put the little negative 1 exponent on it and hit enter. And then I'm going to get that out of decimal form and go into fraction form. The inverse of that matrix is right here. That's our inverse. Instead of writing all that down. I might as well write it. 7 over 4. 3 over 4. Negative 1. Negative 3 fourths. Negative 3 fourths. 1, 1, 1. Negative 1. So you can find the inverse. Now, if you were to ask it to find the inverse and it gave you an error back, what that means is that that square matrix may not be invertible or is not invertible. If it gives you an error, it's the determinant of that matrix is 0, actually, is what it is. But if a matrix has a 0 determinant, it's not invertible. We don't do determinants in Math 140 anymore. We used to do them up until last semester. last spring when they stopped it for whatever reason. But finding the inverse is still in there, even though it's related to determinants. So I figured maybe next year they drop that, finding the inverses out of it. Okay, so solving systems of equations, RREF on your calculator. That's a method you want to try to use there. Recognize no solutions, recognize infinitely many solutions, and be able to rewrite them in the form of the variable that we asked for, usually z. Okay, and then with your matrix, be able to add and subtract matrices, multiply matrices, scalar multiplication, invert matrices. Don't forget to make yourself do a couple of row operations by hand. And 12.2, 12.3, and 12.4 is where we spent most of our time. Page 866. And then 893. So those sections, there's some problems there that you can look at. Odds, obviously, on most of those. So to get some practice with those. Next week we'll meet. We'll finish up chapter 12 and do some nonlinear systems. So a little less calculator work next week. But I thought that this is good for Thanksgiving week. I hope you guys have a great Thanksgiving break. And since it is Thanksgiving week, the quiz for these three sections, even though it will be easy, it won't be due until the next Monday, like not this coming Monday, because I know most of you probably got things to go to between now and next Monday. I don't want you to be, dissing your grandma because Mr. Isbell gave me math to work to do. So that quiz won't be due until the next Monday. Okay, so it's not due this coming Monday. It'll be the first Monday in December that it'll be due. Okay, so yeah, so that'll be good for you to review. All right, you too. You too.